hyperbolas and ellipses are very similar. If you look on the top of 713, it says the definition of a hyperbola parallels that of an ellipse. The difference is that for an ellipse, we use the sum of the distances between the foci and a point on the ellipse is fixed, whereas for a hyperbola, we use the difference of those distances that is fixed. So you might remember that when we talked about the definition of an ellipse, we said that you could go through and it would be like you could put a push pin on the two foci and you could kind of just hang a string in between them. And if you took a pencil and you pulled that string really tight out to the edge and put a dot there and then pulled it over in a different direction and put a dot there and pulled it this way and put a dot here and pulled it this way and put a dot here, that would create that locus or that collection of points. And so maybe for this particular point on the ellipse, this side of the string is 2 inches long and this one's 5 inches long, but it's still going to add up to be 7 inches. Whereas for this dot on the ellipse, this piece of the string is 3.5 inches and this piece is 3.5 inches, but when you add it up, it still adds up to 7 inches. So the idea is no matter where you would pull that, the sum of those two distances would be 7. With a hyperbola, it's not the sum of those two distances, it is the difference between those two distances. So basically, a plus changes to a minus. And so for that reason, a lot of the things about ellipses and hyperbolas are the same, but then others of them are the exact opposite of each other because one's supposed to be a sum and one's supposed to be a difference. So it's very easy to get them confused. And so let's look at our hyperbolas and let's note the things that are the same with ellipses and let's note the things that are different. To begin with, when we're looking at a hyperbola, every hyperbola has two different disconnected branches. So if you have your major axis running horizontally, then you're going to have a horizontal axis branch going this way and a horizontal axis branch going this way. Everything else that you see in here we use to get the hyperbola, but they are not part of the graph of the hyperbola. The hyperbola itself is just this branch and this branch. It looks a little bit like two parabolas. It's not, but it resembles that. If your major axis is vertical, then you can see we're going to have the same idea. We're going to have a branch opening up and we're going to have a branch opening down because they have a vertical axis. All right? So our major axis for a hyperbola is going to be the positive one. That's probably going to be our largest difference between ellipses and hyperbolas. Because you remember, if we looked at the equations of the ellipses, they of course had the plus sign in between instead of the minus sign in between. But when we worked with ellipses, the numerator stayed the same. X always came first, Y always came second, and A and B swapped places, right? That's not going to be the case with a hyperbola. If you'll look at your equations, A and B are staying in the same spot, but X and Y are switching places. That's because with a hyperbola, the major axis is the positive one. So if you'll notice over here, X is positive, Y is negative, so that's why the major axis was horizontal. Whereas over here, Y is positive, X is negative, that's why the major axis is vertical. So we're going to be looking for the positive one to tell me which one is major and which one's minor. Now, A, B, and C all still have the exact same definitions. A is still the distance from the center to the end of the major axis, and the endpoints of the major axis are still called vertices. B is still the distance from the center to the end of the minor axis, and C is still the distance from the center to the focus. But you'll notice that the focus is no longer on the inside, it's on the outside. It's past the vertex. It's on the outside of the vertex. So C is going to be larger than A. That wasn't true with ellipses either. So the equation that relates A, B, and C is going to be different as well. A squared plus B squared will be equal to C squared. So that's just Pythagorean theorem, right? An easy way to remember that is Pythagorean starts with PYTH. And if you'll notice, we've got the HYP right here, PY. We don't have the T, but PYH can help me remember, hey, I use Pythagorean theorem with hyperbolas, and then I just changed the one sign. Instead of addition, I change it to subtraction for ellipses. 2A is still the length of the major axis, and 2B is still the length of the minor axis. But with hyperbolas, those major and minor axes have specific names. The major axis is the transverse axis, and the minor axis is the conjugate axis. So that's new for us as well. Our foci will still be on our major axis, and our eccentricity will still be the C value divided by the A value, but since C is larger than A, as we already noted, when you divide it, you're not going to get a number between 0 and 1 anymore. You're going to get a number larger than 1. Something else about these hyperbolas is that the graph of the two branches is formed by approaching asymptotes. So you can see these dotted lines right here in the graphs. Those are asymptotes. And we're going to have two different ways that we find those asymptotes. The first is you could create the equation for the asymptote, and literally it's just the equation of a line. You could graph that line, and that will be your asymptote. So to get those asymptotes, the equation, if the major axis is horizontal, will be y is equal to k plus or minus b over a times x minus h. If the major axis is vertical, the only thing that changes is instead of it being b over a, it's going to be a over b. But everything else will stay the same. Okay, so when we did ellipses, we said that there were, two different types of problems they would ask us. One, they would give me the equation and ask me to give all of the information. That was definitely the longer, harder application. The second thing was they would give me information and I just came up with the equation, and that was a little shorter and easier. So let's look at our first example. For this first example, they give me the equation of the hyperbola, and they ask me for the center, the vertices, the foci, the eccentricity, the asymptotes, the graph, everything, right? Now, they could have asked me to put this in standard form. They didn't, but if they had given it to me in a form other than standard form, I could just complete the square like we did with the parabolas and the ellipses. All right, so looking at this guy, first thing I need to figure out is which of these two scenarios am I dealing with? So what is my major axis, horizontal or vertical? Which is the major axis? All right, we said that the major axis is the positive one, right? So I can always look at which one is positive, which one is coming first. Y is positive, Y is coming first. So Y is going to be my major axis. It's going to be vertical. Well, hang on. 9 is bigger than 4, and 9 is with the X. If this were ellipses, you would be exactly right. With ellipses, the major axis is the larger one. With hyperbolas, the major axis is the positive one. It does not matter what those numbers in the denominator are. Okay, that's the major difference for us. Okay, so once we know that we're working with major axis vertical, I'm going to copy that equation down here. Here's something else, and this is the reason that I intentionally chose one with a vertical major axis. When we did ellipses, x minus h always came first, y minus k always came second. Didn't matter which it was a horizontal major or a vertical major, didn't matter. The equations were the same. X always came first, y always came second. So when we went to pull out the center, we always could just go opposite of this number, and that was my center. But now with hyperbolas, if x and y sometimes switch places, like if you'll notice y is coming first, I'm going to need to be careful. This is not y minus h. That's y minus k, right? X minus h is over here. So what's h? 3. What's k? Perfect, -1. So my center then is going to be 3, -1, and that's another tricky thing I have to watch out for. All right, if I continue to pair this up with the equation, you can see a squared is equal to 4, so what's a? 2. And b squared is equal to 9, so what's b? 3. Good. Then I could use Pythagorean theorem to find my c value, right? So we could say 4 plus 9 is equal to c squared. So that means 13 equals c squared. Take the square root of both sides and we'll get c is the square root of 13. All right, so let's come over here and plot what we know. We know we have a vertex at 3, -1. We know the major axis is vertical. And we know A is 2, and A is the distance from the center to the vertex. So I'm going to start at my center, I'm going to go up 2, and I'm going to start at my center, and I'm going to go down 2, and those will be my vertices. So again, if you're more of a visual learner, it might be easier for you to draw it out and go, okay, where am I? Well, I'm at 3, 1, and I'm at 3, negative 3. If you're more algebraic, you might have preferred to say, okay, if I start at negative 1 and I add my a value of 2, I'm at 1. If I start at negative 1 and I subtract my a value of 2, I'm at negative 3. That's fine as well. All right, if we start at that same center and b is 3, so if we're going to go out to the endpoints of our minor axis, then we're going to go 3 to the right and 3 to the left. We don't have to name those, but we do need them to sketch our graph. So up to this point, graphing a hyperbola exactly like graphing an ellipse, right? I got the 2 points of the major axis, 2 points of the minor axis. In an ellipse, at this stage, I would have played dot to dot, right? And I would have gotten my oval. Instead, with a hyperbola, I want to make a rectangle out of that. Now, the rectangle is not part of my hyperbola. I'm just using it to help me get something I need. The diagonals of that rectangle will be my asymptotes for my hyperbola. The diagonals of that rectangle will be the asymptotes for my hyperbola. So they had given me equations for asymptotes up here. And they're typically going to require me to give those. You can see we're going to give those down here in just a second. I'm going to have to find them anyway. So if you would rather, if you're going to have to find the equations anyway, if you'd rather make XY charts and plot those two lines using the equations, you're welcome to do that. But you also can just draw the rectangle, and the diagonals of that rectangle will be the exact same thing as if you were to graph those two lines. So whichever method you prefer. Okay, so when I go to draw my hyperbola itself, I'm going to start at the vertex and I'm going to approach the asymptote. So remember, I had vertices at 3, 1 and 3, negative 3. So I'm going to start right here at 3, 1, and I'm going to draw this so that it approaches the asymptote. Same thing, I'm going to start down here at my vertex of 3, negative 3, and I'm going to draw that so that it approaches my asymptote. Now, I need to be careful when I draw those that I legitimately approach those asymptotes. We get this idea that a hyperbola is two parabolas. It's not, but we try to draw it that way. So we come in here and we start right here at this vertex and we come and we wrap it up and we make it look something like this. That is not what the graph of that hyperbola looks like. You'll lose at least 1 point on your graph if you draw it that way. It has to approach that asymptote, so it's going to be pretty flat. Even when you get out here, don't turn this corner up and make it start going up. Again, it's going towards that asymptote. Okay. All right, so let's find our foci. We already know that our C value is the square root of 13. So again, we're going to start at our center. Our center was 3, negative 1, and our major axis is vertical, so we're going to go up the square root of 13, and we're going to go down the square root of 13. That changes my y value, right? So I'm going to say negative 1 plus the square root of 13 and negative 1 minus the square root of 13. If you would rather use decimals for that, you're welcome to. Now, even if I use the diagonals of the rectangle to create my asymptotes, they're usually going to require that I give the equation of the asymptote as well. So remember, when your major axis is vertical, the equation is y equals k plus or minus a over b x minus h. So let's put that in one piece at a time. What was k? Negative 1, right. There it is right there. K is negative 1. What was a? 2. What was b? 3. We identified those right there, right? So that's going to be plus or minus 2/3. X minus h. What was h? 3. Right there. H was 3. Exactly. Now, there's no need to simplify that. You can leave it exactly as that is. If you were going to graph it, of course, you'd want to go through and distribute and combine like terms and simplify it. But if we're just given the equation, that's fine. All right, then eccentricity is still C divided by A, and we've already found both of those numbers. C was the square root of 13, and A was 2. So we'll just say square root of 13 over 2. And if you'd rather give a decimal for that, 1.8 is fine. And again, notice that number is larger than 1, as we said that it would be. So lots of things the same as ellipses, but quite a few things very different. So we've gone through, and anything that was different we've underlined in red to try and help it stand out to us so that we keep those things separate and remember those differences. Okay?